Mike, how are you doing?
It's a great day, doing good. It's nice and cool outside. Looks like fall has finally arrived, and looking forward to going out and doing some yard work this weekend.
Oh yeah. Well, you know, in Canada, I've I've picked up leaves for the past few weekends, and it never stops.
Well,
So
no, never stops.
we're there. All right. So it's 2:02 p.m. Eastern. So let's get this started. Hello, everyone. My name is Johan Uruti. I'm the Director of Technologies for Spartakus and your host, as usual, for these webinars. I'm with Mr. Mike Johnson, and today we're going to talk about lubrication. And I will let my good friend Mike go on to the next slide, if you don't mind, Mike.
Certainly. Okay, there we go.
There. I don't see it on my end. All right, thank you. So, yeah, Johan, Director of Technologies for Spartakus. I've been there for a while, since the beginning. I have 15 years experience in reliability engineering. I have followed some of the classes that Mike gave a few years ago when I started my journey in reliability and lubrication. So, Mike, you want to introduce yourself?
Thank you, sir. Appreciate it. I appreciate the opportunity to visit with everyone today. Mike Johnson, president at AMRRI. I've been grubbing around mill floors for quite a long time, trying to help customers improve the value they're getting, improve their manufacturing efficiency and effectiveness through what can be done with machine lubrication and daily essential care.
Excellent, Mike. So move on to the next slide and tell us, what is AMRRI?
Sure. AMRRI, that's an acronym, stands for Advanced Machine Reliability Resources. We don't sell oil and grease, but everything else related to what we do with industrial tribology falls into our wheelhouse. The majority of our work is focused on helping customers improve their daily care and feeding programs by redefining, sometimes defining originally, the lubrication work plans and programs and helping them get those programs deployed in an efficient manner. We also provide a work management solution called Lubricant that allows management to track completion of daily care and feeding activities, daily lubrication tasks, and generate reports about the completion of task status. We also support companies with lubrication program management. We think of these as project management activities where we are assisting local management through the administration of their workforce to get the machine lubrication activities completed in a timely manner. And we also do an awful lot of certification training. We don't handle all the certification classes, but we do cover the majority of them.
Excellent. Thank you, Mike. And as for Spartakus, well, we are the experts in maintenance strategies, especially PM optimization, asset master data. We have a world-class APM software called Spartakus APM. I invite you guys to check that out. One note, in early October, we joined forces with Reliability Solutions, the experts in precision maintenance and all sorts of reliability and maintenance training. So very happy that our two companies are merging together. So we'll let you know more in the upcoming webinars about, how we're building this big platform for maintenance and reliability. Thank you, Mike.
Very good. Are we ready to jump in?
Yes, sir.
Outstanding. So first of all, I want to let everybody know I'm going to cover more material than is reasonable. The intent here is not to turn you into an industrial tribologist, scientific field of tribology, to make you lubrication engineers, but rather to expose you to the concept at a high level and get into a little bit of the detail so that you understand behind the decisions we're trying to make with our daily, weekly, monthly, routine lubrication activities, that it all should be objectively defined, how we objectively define it, and then we help how we pull programs together to give optimum execution of lubrication activities. So if you hear something you'd like to know more, by all means, send us an email, or if you'd like to get a PDF copy of the presentation, please reach out. We can provide that as well for a resource.
Exactly. And Mike, I'm sorry if I can intervene also. Guys, reminder, it's recorded. So you'll have the ability to go back to that recording once we've put that up on our YouTube channel. So don't hesitate to share that with your friends, family, and co-workers, most especially. Yeah, if you have questions, you can use the chat box to ask your questions, and we'll try to keep a few minutes at the end of this session to answer all of that. So with that being said, Mike, I'll let you go.
Thank you, sir. Appreciate it. So the title of this presentation is A Blueprint for Machinery Lubrication. We're going to start with a very high-level perspective. Along the way, we have all been told that we are attempting to live our industrial livelihood on an oil film that's about 10 microns thick. A micron is a millionth of a meter. If you pull a hair out of your head, cut it in half, measure the gap across it, you got about 70 microns in a human hair. To give you a frame of reference, the fact of the matter is we are not nearly so lucky. All of our element bearings and any machine that has rolling contact actually survives on an oil film between 1/2 and 1.5 microns thick. Journal bearings, sliding surfaces, a relatively more luxurious 3 to 10 micron thick film, both precariously thin layers of protection. The reality is that we are attempting to float our industrial world on an oil film that's at the thickness of a red blood cell. On the one hand, that does work and we get plenty of benefit from it. On the other hand, it is a fragile film. The activities that your folks at your plant site, whether they're lubrication technicians or mechanics or operators, with the oil pail and the grease gun, their activities are all about trying to provide a continuous coating of fresh, clean, dry, properly selected lubricant that cushions and seals and protects machine surfaces from wear and corrosive degradation. If we're able to do that, we win. If something occurs in our daily care and feeding cycle that disrupts that red blood cell thick layer protection, we experience wear from surface contacts, bumping and rubbing. That wear debris, which is a contaminant, produces more wear in the form of abrasive degradation of surfaces, all of which leads to fatigue. And then, of course, depending upon the environment that you have to contend with, there's also the constant challenge of corrosion of machine parts. These degradation modes all impact our ability to produce. It doesn't really matter whether our losses are scheduled or unscheduled losses or repairs, if you will. Once time is gone, it's gone, and we can't get it back. With the loss of machine part function, we lose machine repeatability, which can impact product quality and cost control. We have increased risk of injury anytime we are scurrying around trying to accomplish repairs. Urgent work makes for higher risk of injury. All of that amounts to higher product cost per ton of whatever it is we are producing, and all of that erodes our competitive position in a super competitive industrial world. Our component suppliers are well aware of the predicament that we face. Per SKF, they look at premature bearing failure as bearings that don't reach the L10 life cycle and attribute 57% of the instances of those failures to something that's gone wrong with the machine lubrication approach. Inadequate lubrication is kind of a bucket of excuses. Contaminant specifically refers to sump pollution. Wear specifically refers to the degradation of machine surfaces due to the lubricant not having the guts to provide protection as expected. FAG, Schaeffler FAG bearing says, wait a minute, not so fast. It's actually worse than that. Per Schaeffler FAG, lubricant-related cause shows up in 80% of the instances of premature bearing failure in the form of liquid and solid contamination, insufficient lubrication, unsuitable lubricants been in the machine for too long a period of time. These are basics that we should be attending to with our daily care and feeding programs. Whether it's 57% or 80%, I don't know. But if both of those numbers are wrong by half, it still represents a controllable failure mode, and we have the means to do something to change that outcome. The failure modes that we face are unmeasurable, predictable, and avoidable. We can't control those challenges we face with routine operation of the machine. Okay, so now the question, so what? With all the things that we have to do on a day in, day out basis, why should we put a lot of time, effort, and energy into trying to make machine lubrication work plans better? What's the benefit? Beyond that, to the benefit, what should you expect following deployment of a reliability-focused machine lubrication work plan? Reasonable expectations, 25% reduction of lubricated machine parts over a 3-year period of time, with a target, a big, hairy, audacious goal of 50% reduction in lubricated machine parts. And with all of those machine parts, any labor associated with the repair, any contract labor associated with repair, and certainly reducing the risk of planned or unplanned outages. Ultimately, though, while these top 3 bullet points justify the effort it takes to make a lubrication plan truly focus on improved reliability output, our objective ought to be focused on improving the productive capacity of our operating complex. And a 3% minimum over a 3-year period is entirely reasonable. If we can find a way to reduce failures to the extent that we can add 3% of productive capacity back to our existing effort, then the net benefit of this changes our competitive position entirely within our industry, whatever it is that we have to be competing in. There's a variety of ways you could point to increased productive output. Here's a chart, a results benefit, 8-year study, aluminum rolling facility in Australia, where they shifted mill speed from 46 meters per second to 103, and then ultimately 120 meters per second of mill time or mill speed. At the same time, accomplished a substantial decrease in the amount of bearing replacement. And the lubrication impact here was found through substantial improvement in sump contamination or sump pollution control. Substantial increase in productivity, both from increased mill speed plus reduced failures. Here's an integrated steel mill study from Nippon Denso Steel in Japan over an 8-year period. Program implementations, the red dotted line, and reduced component replacements for hydraulic systems parts, showing a correlation, increased pollution control, contamination control, program effectiveness leading to reduced repairs. Kawasaki Steel, not to be outdone, reduction in fluid consumption and breakdown frequency over a 5-year period. There's a variety of ways that one can measure success. Perhaps it's just hard, cold dollars. Here's a study showing 3 years following overhauling the machine lubrication program. The work was done in 2015, and the benefits were accounted in 16, 17, and 18. Our financial elements within our facilities are interested in knowing what the power of the investment would be in terms of returned money. So the bottom line here, really the bottom line, 3-year improvement expenditure, $500,000. 3-year estimated savings, $8,800,000, 1,553% return on investment. Sometimes it's just about the money. And machine lubrication work practices improvement is truly a best buy in industrial cost savings opportunity. There's also a safety improvement element. Well-established relationship between asset utility, the green line here, and injury rate risk. And we know from plenty of examples, as our asset utility improves, our risk of injury declines. And this chart shows the flip is the opposite is true as well. As that asset utility measured by overall equipment efficiency declines, the risk of injury increases. There's a strong correlation between PDM work orders, such as machine lubrication, vibration data collection, inspection, and minimizing risk of injury. There's a strong correlation between reactive work orders and increasing the rate of injury. As you think about these potential benefits, and you think about where you are with regard to your competitive position, with regard to your work injury incidence rate, you've got to holistically look at your program, all of maintenance, and beg the question, what is our system providing for us? Per W. Edwards Deming, your system is designed to give you the results that you get today. If you want different results, you've got to think about the system. So with regard to improving machine reliability and really improving overall maintenance through lubrication program development, it's a step-by-step exercise. None of this is necessarily easy, but it's all entirely accomplishable. Step 1, measure the current state of affairs. Step 2, build a plan following that measurement, come up with a plan for development, and then step into that plan. Oftentimes, and for the part of our presentation today, it involves taking a new, fresh, hard look at what products we have selected, how often, how much, how we will go about conducting daily care and feeding of our machines. Step 3, use the oil-based sampling program to create a feedback loop that gives us an understanding whether we've accomplished our objectives defined in Step 2. Step 4, make necessary capital improvements. There's a lot of things that can be done at a very low cost to improve overall reliability of the machines. And Step 5, consider upgrading the overall knowledge base of folks that are involved in this particular operation of our maintenance routines. Let's focus on Step 2 for just a little bit here. When we step into reorganizing the machine care plan, machine lubrication care plan, you got to realize it is a detail-intensive activity. We're going to go get a lot of information about the machines, their components, size, shape, and speed of components, the operating context. And we need to have a way to go about managing this large amount of information that is going to drive the decisions that we will make to make improvements. Secondly, whatever we come up with, we need to be focused on machine health first, and the lubricant that is the choice second. Now, traditionally, lubricant vendors have provided these kinds of work activities, and as it is their right and their responsibility, it tends to be a focus on what lubricant goes where. But a machine lubrication program is very thorough, goes well beyond just what lubricant goes where. So we start thinking about machine first, we have to dig into the machine details. What details do we need to build a new plan? And then beyond that, as we think about the details, we should beg the question, how much time do we need to accomplish these details that we're going to be presenting as a new basis for daily care and feeding? Now we have a poll question here.
All right, so
Okay.
the poll will show up on your screen, guys. So just let us know, how do you know how much labor you need for your lubrication program? And it's based on an annual fulfillment, so please let us know. And once you've entered your answer, you'll see the results showing up on the screen. So I don't know if you can see that on your end, Mike, but at the moment, At the moment, the top answer is task type calculated. We've got more than 50 people, 50% people that of the people that have answered task type calculated.
Good.
We've only have 5% on the scientific guess, and the rest is no idea, or we don't have any dedicated lubrication technician.
Okay. Yeah, that's certainly a fair answer.
Mm-hmm.
Shall I proceed?
Yes, sir.
Those that leaned into the notion of task types, I think you're right on target. So when we set about to redefine our daily care and feeding program, sorry. Okay, we set about to redefine our daily care and feeding program. It's not a focus on the whole asset. It's really a focus on subcomponents, and really it's subcomponents. For instance, we should never lubricate motors. Now, we do want to lubricate the bearings, inboard and outboard bearings, but we really don't want to push it so hard that we're getting lubricant on the internal surfaces of the other motor parts. So it's a sub-component function that we're really measuring, time stamping, and thinking about. Let's take a simple example, process pump. We had inboard and outboard bearing motor bearings, coupling, which may or may not be lubricated. Let's assume it's critical pump and is lubricated. And then we have the pump body itself. Now we have a couple routines to accomplish with the pump body. A level check and top up, perhaps a sample, eventually an oil change. When we start to tabulate the tasks that must be completed for any given asset, we look at the sub and sub components. We got a motor that has two bearings, and let's assume just on average, we're lubricating the motor bearings twice per year. So we have 4 events, and each event requires a time allocation. The coupling, 2 events per year, and a time allocation for those. The routine level check and top up. It's very common for folks to do level checks on a weekly basis. So we get 52 events, typically getting a 2 to 3 minute time stamp. The sample exercise, if it's a critical machine, we should never push it out beyond 3 months. So let's say we have 4 samples per year, and then eventually an oil change factored in. A simple, single, critical process pump could tabulate 63 tasks in a given year. We need to allocate a timestamp for each of these tasks and then multiply that timestamp times the number of events in order to know how much labor needs to be set aside for a single critical pump. A single critical direct coupled FD fan, different set of components. We got the motor, we have coupling, we have shaft bearings, and let's say it's a decent sized bearing turning at a decent speed. We end up with 12 visits per year to lubricate each of the 2 bearings, 24 tasks, 30 tasks total per year. A more complex machine, a critical conveyor with all of the various different components. We tally up all the individual task visits to the machine. A belt conveyor can have, whoops, sorry about that, guys. Too many buttons there. Put it back in presentation mode. A single critical conveyor can have 204 discrete tasks, each task with a timestamp. It doesn't take long when we tally up even a relatively small operating deck, 30 conveyors, 30 fans, 500 pumps, not a very big facility, but we see the total number of tasks that pile up over the course of the year, 39,420 tasks. That takes time. Each one of those has a timestamp allocated. And then once we have gone through and defined each of the details, allocated time for each of the tasks, we have the means to come up with an annual and then on a week by week routine weekly labor requirement as well. The double is, of course, in the details. And we do need to sort through the details to come up with a very strong management plan for this task-intensive kind of activity. So when we go out to look at the machine parts, I said earlier, it's a machine first thing. So we'll start with the machines. We're going to create a floor plan that shows where the machines are, and this becomes the basis for the efficient route. We'll record machine name and number, log the individual components by type and meaningful nameplate and design details, and then lastly, observe the environmental characteristics around the operation of the machine to capture those influences in as much as the operating environment has the effect of degrading the lubricant life cycle. So step one, create a floor plan that shows the physical location of each asset. With a floor plan in hand, step two, sit down with the technician and perhaps the supervisor as well, and create a linear sequence that represents the route structure that ought to be followed for whatever technician and or operator is in the daily care and feeding work plan. So we have an efficient plan. Ultimately, this activity should deliver efficient routes. Once we have the linear structure in place, then we can go back to the machines and collect specific information as is needed to identify the care and feeding plan for each component. We got a motor and a coupling, a gear drive, it's got a breather, it's got a sample port, it's got shaft seals on each side. We have a coupling to a drive shaft. The opposite side, we have a backstop, externally mounted backstop. Each one of the lubricated components in each one of these subsystems of the drivetrain needs to be accounted for. Kind of information we're looking to collect. The motor, well, not just the motor, but the number of elements in the drivetrain, who made the components, the elements of the drivetrain, how many are there, how many lubricated parts are there for each of the components, what's the component type, in as much as that defines the lubricant type and the chemical family for the lubricant. And then lastly, the make and model number of the components. And this last piece is an essential bit of information that's needed to objectively define what should go into the new machine care plan. We also need to identify, for whatever other component type, the size, the speed that that component is working, general loading conditions, although we accept if there's a component in the machine, it's the proper component as selected by the machine designer. We are not actually trying to make adjustments in load rating calculations when coming up with a care and feeding plan. And then lastly, the environment where the components are operating. Mostly the information that we would use to pull a plan together comes from a physical equipment inspection. OEM guidelines may come into play, ASTM or other ISO standards perhaps. Component-specific OEM guidelines beyond the machine designer, builder-specific OEM guidelines, and all can have a role, but mostly it comes from a physical observation of the machines themselves. Take a look and see what that actually looks like in real life. Suppose we're looking at a pump. We start with a motor. We observe the bearing numbers for the load side, that's the bearing closest to the coupling, and the opposite side. These ISO or DIN standard numbers tell us what the component type is, ball bearing, the gauge value, the dimensional characteristic. These last two digits, when multiplied by 5, gives us the bore dimension. And on that, we can look up this number on a table and come up with all of the bearing dimensional attributes that are needed to go along with the speed, rotating speed of the asset that will define the lubricant requirements for the component. So let's walk through this and see what that actually looks like. First question we want to ask is it going to be okay to lubricate this bearing with grease? Oftentimes we have components operating on grease because the OEM said, use grease. When in reality, we go to the component designer, we can run through a simple scenario, calculate whether that component is going to be safe to run with grease and expect to achieve the net total life cycle or not. And you get to looking at all of your machines at your plant side, you'll probably find some instances where you have bearings that are grease lubricated that really should not be grease lubricated. Step one, determine if grease is going to be okay. In order to do that, we're going to find the NDM, shaft speed times the bearing's median diameter. This is a calculation, shaft speed times median diameter. The details come from the bearing itself. This is a bearing furthest from the coupling, 40 millimeter bore, 80 millimeter OD, added together, divided by 2, gives us the median diameter times the shaft speed, gives us the speed limit for this particular operating bearing. Do the same thing with the bearing closest to the coupling, the 6300 series bearing that we looked at. We compare the numbers that we see, 113,000 is the highest number, to what is considered tolerable for ball bearings, and it's a pass. Yes, as long as the number we come up with is below the speed limit value, it's safe to lubricate with grease. We notice that there's different numbers for each of the other different bearing types here, so there's no one number for all ball bearings, for instance. It's specific to the operation of the bearing. First question, is the speed acceptable for grease? We compare our actual NDM value to the speed limit by the bearing manufacturer. We come up with a decision. Step 2. Step 3, now that we know it's safe to lubricate with grease, or perhaps even if it's not, we got to figure out what the dynamic viscosity should be for the operating conditions that we face. The minimum allowable viscosity is 27,878 times the shaft speed of the machine, the negative 0.7114 power, times the bearing's median diameter, the negative 0.52 power. These details, or this formula, comes from the bearing manufacturing community. We run the numbers, come up with some values. We come up with a minimum allowable viscosity as needed to make the bearing elements float in the races. We round it. We multiply by 3 because we don't like drop dead viscosities. We need a little bit of fudge factor. We need a little bit of room for temperature excursion. So we multiply this minimum by 3 to come up with a target. That's step 3. Step 4, we look at the lubricant that's in use. And let's say it's the Chevron SRI electric motor grease or Polyrexia electric motor grease, 2 very common, very good quality electric motor greases. They have an ISO 100 viscosity grade used to make the grease. Let's say that the operating temperature for this pump or fan bearing is 50 degrees C, 122 degrees Fahrenheit. This grease with an ISO 100 viscosity grade base stock at that 50 degree temperature gives us 60 centistoke of working viscosity. Now, previously we said we have to have at least 47.2. We have 60 centistoke, so we're at 5 times the drop dead point. We're in good shape. That means that the product that's been picked is in fact fully suitable to give us expected bearing life cycle. Little bit of extra detail. We're looking for a best fit in the lubricant selection decision, whether it's oil or grease. We want a value that's between 3 and 5 times that drop dead minimum value. So we look at each of the products based upon the viscosity grade, standardized viscosity grade at operating temperature to come up with the value that we're looking for to justify that the product we picked is the right product. Step 5, now that we know that the viscosity is correct, the product for the electric motor is correct, let's extrapolate this to all the other bearings in our facility. Electric motor greases do not contain EP and anti-wear additives as a primary focus, where your rank and file general purpose grease is going to be pretty well loaded with EP and anti-wear additives. So you've got to decide whether or not any bearing that you have operating out there should be fed with EP, AW additives, or per the bearing manufacturer's preference, just operate with an R&O chemical family. And the deciding factor becomes that drop dead viscosity calculation that we talked about. If we can pick a product at operating temperature that is on the right side of this drop dead line, this is 1 times required viscosity, then we should lean away from the EP characteristics. If, on the other hand, we don't have a choice and we know that the product we pick is not going to give us the full oil film that's needed to float the components, then we consider leaning into the EP in order to try to achieve some of the expected bearing and reliability expected life cycle. Step 6, once we know that the product we picked is the right product and the right chemical family, next question becomes, all right, how much should we actually apply? This is not guesswork. Here's a formula provided by SKF that makes it really simple. The width of the bearing, millimeters, times the OD of the bearing in millimeters, times the space factor for millimeters, 0.005, gives us the volume that should be used to flush out the quantity that exists between the inner and outer race and between the 2 axial planes of the bearing itself. So, dropping in the numbers from our motor, the bearing that was furthest away from the coupling needs 7.2 grams. The bearing closest to the coupling, slightly larger bearing, needs 10.2 grams whenever we decide to feed the bearing. The next question then becomes, how often should we feed the bearing? The couple different ways to go about validating that product type, that product selection, and the volume is good. We strongly encourage coming up with a set value and then using some kind of a meter to make sure that we are getting to that point and stopping, not over lubricating the components. The next question then is, how often should we be feeding the bearing? What we would like to have, if it's grease, is a itty bitty little bit put in very often. Oftentimes we end up with long and non-standardized feed intervals that leaves us in a spot between oversupply and undersupply around our lubrication cycles. We really like to have a flat line here that is a constant flow, which is kind of what we get when we're lubricating with oil, but not so much when we're lubricating with grease. So using a DIN standard basis for coming up with a frequency, there is a formula. The information inside first set of brackets comes from the bearing itself. The information between the 2 brackets comes from the operating context, bearing temperature, atmospheric contaminant load, moisture load, vibration, shock loading, impacting events that may be present with normal operation of the machine, whether it's a vertical or a horizontal shaft orientation, and then the bearing itself are all influences on how often we should be lubricating the bearing. 20 is a plugged value. We drop the numbers into the formula here and we come up with operating hours between lubrication events. Now back to this point here, if we think that we need more grease than we're going to get based upon the calculated value, then we can always prorate this to a shorter interval, prorate the grease flow according to that shorter interval, and make adjustments along the way. Sometimes we have so much water that we need to use grease to push water out of a large pillow block housing with labyrinth seals. So we just want to use the grease as a media to push the contaminants away. Well, we don't get the full benefit of that water excursion challenge with the normal calculation. So we rationalize it according to our experience with the components there at the plant site. Whatever we end up with, we do have the means to use technology to validate our work plan for element bearings. Compression wave analysis, also known conventionally as ultrasound, is a measure of contact energy that occurs between the 20 and 100 kilohertz range. Contact energy is created by impacts. Here I'm illustrating what happens when there's an impact between 2 metal pieces. A compression wave is created upon the moment of impact, and that can be collected, measured, and tracked. Inside of a bearing, if the oil film gets too thin, the asperities that exist begin to bump and rub. This creates contact and that contact can be measured. And the thinner the oil film, the greater the contact or ultrasound energy is produced. So this is a fantastic way to go about validating that our lubrication daily care and feeding plan, or weekly or monthly, whatever it might happen to be, is in fact giving the bearing everything that it needs for maximum long-term use. So there's rules for element bearings. There's rules for journal bearings. There's rules for couplings. It's based upon the components themselves. Here we have a chart showing the centrifugal force that's applied to the grease inside the coupling. Got a shaft speed defined, and the coupling pitch diameter defined, and even a relatively small coupling turning at 500 RPMs is capable of producing exceptionally high centrifugal forces. That centrifugal force literally squeezes the oil right out of the thickener for the conventional lubricant. So couplings require specialized products. There's, per the American Gear Manufacturers Associations, different grades of couplings allowing for speed, misalignment, torque, peak torque, and other conditions. For each of those AGMA coupling grades, there is a grease quality associated with that. There's also rules for gear drives. Much like the other components, the driving influences the speed with which the gear face, the gear wheel is turning, and its calculated value, pitch diameter in millimeters times the speed that gear wheel is turning divided by a constant factor. There's an AGMA standard that gives us elaborate information that is useful to figure out exactly what we need if that's not provided by an AGMA approved gearbox manufacturer. Here we have a table from the chart, table B3, where we're looking at a synthetic type of lubricant for a given pitch line velocity. We have a viscosity grade. It's a correlation between the temperature of the oil in the sump and the pitch line velocity of a given gear wheel in operation. So it's all very narrowly tied down. Just as a point of notation, the pitch diameter is the gap between where the gear teeth transfer the load all the way to the opposite side for the pitch circle. That's the pitch diameter. Fortunately, our gearbox manufacturers have done a very good job, responsible job of putting the information that's calculated onto the name tags. We get information that looks like this. Ambient temperature of 15 to 60 degrees, use an AGMA grade 4, viscosity between 135 and 165 centistoke. If it's a higher ambient temperature, we use a thicker oil, and AGMA provides insight when it should be R&O chemical family versus EP chemical family, and even when we should be leaning into a synthetic for optimum long-term gear function. So there's a bunch of details we have to collect. So we collect the details, we run some calculations, and we drop those calculated values into our daily care and feeding plan. Here we have another poll question.
So how objectively defined are your lubrication practices, guys? Let's see what the answers are. So we've got a fairly good is predominant for now. Yeah, we're around 60% fairly good practices there, Mike.
That's good. That's good.
And just a couple of you said it is top notch. It's good.
That's great. Along the way, industry is getting smarter and smarter about the value of whatever we got to do to protect that blood cell thick layer of protection. For our part, when pulling the details together, like I said earlier, we're going to collect a lot of information. So this is where a computer can come in handy. We have a chart that we fill out that shows us the basic bits and pieces of information that must be collected and aggregated in order to make those calculations and completely objectively define what the daily care and feeding is going to be. We organize the details, of course, around machine normal, CMMS, hierarchical structure, equipment name and number. Then we get into the details, component and additional text to describe the components, the number of components, their capacity, unit of measure. We don't stick with shots since that's not a standard unit of measure. And there's 200 different grease guns on the surface of the planet with differing values for quantities per stroke of the hammer. So a standardized unit is always the best bet. The number of locations where that lubricant goes, how it's applied, the product that's in use, manufacturer, make and model number, task type, regrease, repack, level check and top up, oil change, the frequency, whether the machine's running or not, the route. Then in the route structure here, this is number 1 in the route, number 2 in the route, number 3 in the route, number 4, and so forth. So we build out the routine task requirements according to that dotted line that we looked at in the very first step. The timestamp, you've got to have a time, a duration in minutes for each one of these tasks that will give us the means to aggregate and come up with an annual plan, and then also look at our weekly to monthly labor requirements, see if we are providing enough labor to get the whole job done. Then lastly, a work practice or procedure. Excuse me. With the amount of turnover that our industrial world's experiencing these days, and really robustly since COVID fell upon us, we have a lot of new people that are entering into a variety of different work functions, work modes. This particular work mode is not something that we learn in high school or college. It's pretty much an on-the-job kind of thing. And if, when, wherever we can provide a defined procedure for how to go about fulfilling that work, then the newbies that are joining the crowd, new employees to this work mode, then have a basis from which they can expect to get things done according to the company's plan. It's useful to have a task management system. Given the great number of tasks that a typical industrial facility has to manage over the course of the year, it's useful to drop it into a computer where we have a hierarchical structure, the department and all the machines in the department and all the details and data fields that can then be turned into route statements, statements of tasks to be accomplished, that can then be turned into a weekly scheduling routine where we might have 24 activities that are scheduled all at one time in a batch, but the computer has the means to identify anything that's overdue, identify what's currently due, and even give us some feedback in the means to auto recycle any tasks that get missed for whatever good reason. The information can be printed out to a sheet of paper, can be dropped onto a tablet, just depending upon user preferences. I'm an old guy myself. I prefer to read a book from a book, not from a computer. So that's just a natural preference for me. There's a lot of folks out there that would just as soon have a sheet of paper, but whether it's paper or tablet, it's just a function of the nature that the information will be provided to the workman. If you're using a task tracking system, then you ought to be able to generate customized reports that give you very specific understanding of who got what accomplished, who got what missed, who found something that wasn't in the schedule that got accomplished, and these kinds of very important details. Machine lubrication work quality, the quality of the plan, begs for us to apply a relentless focus on nitty-gritty details. We ought to have robust KPIs that give us the means to track the daily care and feeding of the machines with ease. Wherever we are, there's always room for improvement. KPI should evolve around weekly compliance, KPI stands for Key Performance Indicator, in case that's a new acronym to you. Oil analysis compliance, including, are we below our contamination control targeted values? Are we within acceptable oil health control limits? There's always room for improving a knowledge base in this particular field. This didn't become a technical field until 1966. Colleges, two-year colleges, universities, high schools, we don't teach industrial tribology, applied tribology. So this is something we need to learn on the job, and it's vitally important. It's the beginning of mechanical failure prevention. Now, once we have our program defined and operating in high quality order, quarterly reviews to stay abreast of changing reliability goals and expectations for the operation itself. The cornerstones of mechanical reliability, as we all know, depend upon a precise installation of the machine and precise balance and precise alignment of the rotating shafts in the machine. All this precision is brilliant and necessary. And we do a pretty good job of getting these things right these days in our industrial practices. But if we forget the daily care and feeding, if we forget to apply another layer of precision lubrication, then this cornerstone activity that we're careful to deliver really much of that value can be lost. I'm going to step back to the 30,000-foot view here for just a second. I've thrown a lot of details at you, and the details have merit, but let's think about something in very generalistic terms. You have a maintenance budget, and there's major sections of your budget. You got labor, which is both overtime labor and base labor and wages, and you have materials, which is a combination of miscellaneous things that you use in maintenance, but it's not part of the product, and money that's spent by the purchasing department for machine parts and building parts. About half of the 40%, the largest line item in the maintenance budget, goes to purchasing parts associated with rotating equipment. So the lion's share of the, I should say, an equal share of the components value associated with rotating equipment. You have a small slice in your maintenance budget that pertains to lubricant purchases. If it's a chemical plant, 1%. Cement mill, paper mill, 2%. Steel mill, integrated minerals, mining, processing, 3%. A relatively small proportion of the total. The funny thing is, how you use that 1% directly impacts net base labor and wages, certainly overtime labor, and certainly the money that's spent to buy rotating equipment components. So your 1% or 2%, whatever it is, has an impact on about 35% of your total maintenance cost. That's called leverage. This thing, this ho-hum machine lubrication, daily care and feeding thing that quite often is considered a necessary activity, but not a desired activity. This thing gives you great leverage over the other costs associated with your maintenance activities. Last words here. There's a strong relationship between the quality lubrication program and the frequency of replacement of lubricated machine parts. If you're experiencing a high frequency of lubricated machine part, there's an element of your lubrication program that can be tuned to help you remedy that. Machine lubrication is best buy, fantastic leverage. 1% of your budget gives you 35% leverage over other costs. You have to have the details and the means of discipline to manage a large amount of information when you set into this pursuit. Okay, that was a lot of stuff. Very quickly, a lot of details. If you have any questions, here's my email address. Here's Joanne's email address. Please do email us, copy both of us, if you would, if you have any questions, and we'll get back with you promptly.
Thank you, Mike. I've given this lubrication trainings in the past, and in just an hour, you summarized what typically is given out in, let's say, 8 or 12 hours. So good job, Mike.
Thank you.
I want to give the audience the opportunity to ask some questions to Mike.
Sure.
If not, I have a couple questions, but just feel free to ask. Volunteer. All right. No
Yeah,
volunteer.
question.
Oh,
Mike,
yes.
what's your experience recommendation on maintenance techs performing lubrication versus having a dedicated reliability tech?
If your maintenance techs are assigned to and expect to be held accountable to that task and know they have to get it done, that'll work. If you have maintenance techs in general, i.e., well, all mechanics are responsible for machine lubrication, then following a simple human frailty here, if everybody is responsible for something, no one is responsible for something. This is an area where people operate independently. There should be assigned expected responsibilities. I, for one, would always look for have dedicated lubrication technicians where they've got assigned areas, assigned tasks, they're measured weekly, and they have the freedom within a well-defined program to get all their stuff done and done properly. And if they can't manage that, then we need to find a different resource.
Thanks.
Yes, sir.
All right. So, Mike, I have a question for you. So, you've implemented lots of lubrication programs. I'm wondering. I kind of know the answer, but I want to hear it from you. What is the top challenge or top 3 challenges in implementing a world-class lubrication program in this, and most importantly, in sustaining a world-class lubrication program?
Yeah, coming up with the plan, it's time consuming because it's machine parts that have to be studied. And it just takes time to go look at all the machine parts. And if you have an understanding of what your timestamps are going to be and how to go about validating lubricant that's in use and all those kind of things, it just takes time, but that's not especially complicated. Sustaining the program after it's deployed really requires senior level management being willing to participate by asking for results. Establishing strong key performance indicators, 4, 5, 6 of them is plenty, and then asking for feedback on fulfilling those key performance indicators of the management team and the technicians, and asking for that feedback on a routine basis. A weekly report sent to senior management where they can say, this is pretty good. We got 95% of our tasks done this week. What do we need to do to make sure we can get all the tasks done? Having senior level interest in this program is essentially important in order to sustain it. And the senior management is not investing time in asking, how are we doing, guys? Then it won't be long before no one is asking, how are we doing, guys? And then our compliance is left to the personal commitment of individual mid-level managers. And those guys move around a lot. Biggest challenge I see lately is movement of supervisor from a role to another role, or from one company to another company, and it kind of breaks the chain of command. And the guys that are out doing the work aren't really interested in having a new chain of command with new accountability focus and what have you. And so, the disruption of the process means the program then falters.
Yeah. So human factor, to summarize.
Human factors, absolutely.
All right. Thank you, Mike. It's already 3 p.m. Eastern time. So again, thanks everyone for your participation and being there. So if you have any questions, feel free to reach out to us. We'll have the recording available to all of you. Mike, if you want to go ahead and show the last slide, as usual, well, you know, we do these webinars on a monthly basis. Next webinar, next month, we'll talk about planning and scheduling, so work management, and we'll talk about the top 10 work management errors. So we'll be with our expert, Michel Côté from Laurentide